Welcome back. In this lecture we are going to start elementary fluid dynamics, or more commonly Bernoulli's equation. So we are going to cover some basic derivation in this regard, and then we proceed further to some of the solved examples. So we are going to see the Bernoulli along a streamline. So if you remember, this equation we had got from in the last week's lecture, that is on fluid statics. Okay. So if you, I am just going to draw a streamline. This is I direction, okay, this is J direction, and this is K direction. It's better to take away all the ink, I should, and this is the S direction is the streamline, I mean the direction of the streamline, and this is normal to the streamline. Okay. So we have to separate the acceleration due to gravity, and coordinate axis here can be in any orientation. This is quite important to understand. K is vertical, S is in the direction of the flow, and is normal to the flow. That is our standard assumption that we have been taking. So this equation, when we start writing down, in the component form, so delta P in the S direction will be minus del P by del S is equal to rho into acceleration, and this G, in that we have to take the component of G in the direction of S, and that can be written as rho G dz ds. Okay. So that is the component of G in S direction. Okay. So we have to note that there is no shear forces there, the flow must be frictionless. Okay. This is also a steady state, so there is no change in P with respect to time. P is pressure. Okay. So the equation that we have obtained is minus del P del S is equal to rho As plus gamma dz ds from here. So rho G is gamma. Okay. Going back to the slide again. So this is what we have got, minus delta P delta S is equal to rho As plus gamma dz ds. Good. So can we eliminate this partial derivative? Yes. So As is actually the total derivative dv dt, right, and this can be written as del V by del S multiplied by ds by dt, and this can be written as V del V del S, or del S del V del S into V. Okay. And this is obtained through this way of doing this, this differentiation is called the chain rule. Write acceleration as a derivative with respect to S. So the total change in pressure can be written as dP is delta P delta S into ds plus delta P delta N into dN. So N is constant along a streamline, so dN is equal to 0, therefore this term goes. So dP by ds can be written as del P del S. You see, now this is the total and this is the partial. Okay, that is why we are able to write this. Okay. And dV ds is written as del V del S. Okay. All right. So this equation turns out to be minus dP ds, because this is what we have proved. Okay. From here, and dV ds as del V del S, or the opposite. So we can write rho V dV ds plus gamma dz ds. As is V del V del S, and instead of del V del S we can write dV ds. So this is the equation. Okay. Now we have to use force is equal to mass and into acceleration along a streamline and integrate it. So this is the equation that we have, right? So what do? We integrate it. First eliminate ds because it's common. So we can write dp plus rho v dv because dp will come this side plus gamma dz is equal to 0, and if we integrate this will become dp. So what we do is we divide by rho so that this gamma becomes g. It will become dp by p plus v dv plus g integral dz is equal to 0. Okay. Here the density is a function of pressure. Okay. So we have to keep it inside. So we write integral dp by rho plus v square by 2 and gz is equal to constant. If density is constant, we can write p plus half rho v square plus gamma z is equal to cp. All right, I will take down. So what we have done, so we have written the equation along the streamline, applied force is equal to mass into acceleration along a streamline, integrated it, and we have obtained Bernoulli's equation along a streamline. Okay, this is one of the ways of the derivation. Okay. Now the Bernoulli's equation, the assumptions that are needed for Bernoulli's equation. What have we assumed? The flow was frictionless, the flow was steady. The final equation that we have derived, we have assumed constant density, that means the flow was incompressible, and we have done it for along a streamline. Now can we eliminate the constant in Bernoulli's equation? Yes. If we apply the Bernoulli's equation at 2 points along a streamline, this is important. So the streamline should be the same, and if we apply these equation along two streamline, to 2 points along a streamline, the constant would be the same and therefore it can be eliminated. Bernoulli's equation does not include mechanical energy to thermal energy conversion, heat transfer or shaft work. Okay, so this is some general information about the Bernoulli's equation that you might be aware of from before. Now the Bernoulli's equation is a statement of conservation of mechanical energy. So you see P by rho plus G by Gz plus half V square. So this is potential energy. So let me take the eraser. And this is, this is kinetic energy. Okay, I'll take down the ink again. Okay, so P by gamma plus Z plus V square by 2G is equal to Cp, where P by gamma is the pressure head, Z is the elevation head, and V square by 2G is the velocity head. Okay, good. And we can also say, that P by gamma plus Z is hydraulic grade line, HGL, very common concept in your fluid mechanics class, or piezometric head, whereas P by gamma plus Z plus V square by 2G is called energy grade line, EGL, or total head. This is something that you can be asked, by anyone, whether you are giving a gate exam or an interview, sitting for a company which works in hydraulics. So you must be remembering what hydraulic grade line is, what is energy grade line, what is piezometric head, what is total head. Okay. So now proceeding forward, first simple case, very simple case where V is equal to 0. Okay. So this 0.1 and this 0.2, Z direction is shown as above. This is pressure datum and this is elevation datum. Reservoir means V is equal to 0. Okay. So now, as I said, this 0.1 has been put on surface and we can put 0.2 anywhere. We have decided to put at this random point. Okay, 0.2, point number 2. So we apply the Bernoulli's equation between these 2 points. So in the reservoir the velocity is 0, right? So V square by 2G is going to be eliminated here. So between these 2 points we can write P1 by gamma plus Z1 is equal to P2 by gamma plus Z2, whatever it is going to be. We also know that P1 is a gauge pressure and this is a pressure datum, atmospheric pressure. So P1 will be 0, right? In our second case, so we can write Z1 minus Z2 is equal to P2 by gamma, because elevation datum is here, so 2 is anywhere. Here we did not cross any streamline, so this analysis is okay. If we keep crossing the streamlines, then what happens is this equation is valid for 2 points on the same streamlines. You cannot cross these streamlines. So this analysis, Z1 minus Z2 is equal to P2 by gamma. This is exactly the same analysis which we have found using the statics lecture, if you remember from last week. Great. All right. So proceeding forward. So we take another simple case where pressure is 0 or constant. What is an example of fluid experiencing a change in elevation but remaining at a constant pressure? It's an example is a free jet. What is a free jet? This can be taken as a free jet. You fill a bottle with water or any fluid and make many holes. We saw similar type of figure last week as well, and you see there are jets of, the free jets, this one, this one, this one, this one as well. I'll delete that. Yeah. So the equation, Bernoulli's equation along one streamline will be P1 by gamma plus Z1 plus V1 square by 2G will be equal to, at any point 2, same, P2 by gamma plus Z2 plus V2 square by 2G. Because this is atmospheric pressure at point 1, we assume the point 1 to be the free surface there. So pressure at point 1 will be atmospheric, therefore 0. Similarly, if we consider any point along the streamline, what's going to happen is right. So what is going to happen is P2 is also exposed to atmosphere and that is also 0. So we can write Z1 plus V1 square by 2G is equal to Z2 plus V2 square by 2G. and therefore the velocity at 2.2 will be v1 square plus 2g z1 minus z2. Okay, where v1 can be the velocity, fall velocity of the surface. All right. So we talked about, but if we talk about hydraulic and energy grade lines, the question is the 2 centimeter diameter jet is 5 meter lower than the surface of the reservoir. What is the flow rate Q? Let us draw a figure like this. Okay. So this is the elevation datum here. So the equation, Bernoulli's equation is P by gamma plus Z plus V square by 2G is equal to constant. Okay. We have to conserve the mechanical energy. Okay, that is the energy conservation. So to make it less cluttered, I will delete this annotations. So pressure datum is atmospheric pressure, very simple, because both at the outs at here or here. So the jet solution. So the question, again coming back to the question, the 2 centimeter diameter jet is 5 meter lower than the surface of the reservoir. What is the flow rate Q? Again drawing the same figure. This is the elevation datum. Therefore Z2 is 5 meter below, that is what it says, 5 meter lower. Are the 2 points on the streamline? Yes. So we can write P1 by gamma plus V1 square by 2G plus Z1 is equal to, so these are the 2 points, just that if you are confused. Okay. So P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2. P1 by gamma will be 0, there is no velocity at, this is at rest, right. So the velocity is also 0, and there the datum is also 0, because we have set the elevation datum here. Okay. The pressure at 2 will also be 0, atmospheric pressure. Now there will be a velocity, okay, and because there is Z2, so V2 will be under root 2G minus Z2, and the discharge will be pi d2 square by 4 if d is the diameter, 2 centimeter diameter jet it says, okay, under root 2G minus Z2. Very simple applications, but it is important to apply it to these cases. So this is our two results, V2 and Z2 is minus 5, so you can obtain the it will be approximately 10 meters per second. For example, if you assume G as, if you take 10 meters per second squared, V2 will be under root 2 into minus 5, so that means plus 5 into 10. So V will have to be 10 meters per second. Okay. All right. So one of the other applications of Bernoulli's equation is the stagnation tube. What happens when the water starts flowing in the channel? For example, this, okay, and so the equation along a streamline, Bernoulli's equation can be given as P by gamma plus Z plus V square by 2G is equal to constant. Okay. Here the orientation of the tube is like this, but does the orientation of the tube matter? Yes, because it can either lower up, it can change the different value of Z. So yes. How high does the water rise in the stagnation tube? That we have to calculate. How do we choose the points on the streamline? Another important question that we will solve. Okay, so we assume points 1A, 2A, 1B and 2B like this. This point, this point, this point and this point. The equation, Bernoulli's equation will be the same, P by gamma plus Z plus V square by 2G is equal to constant. So if you go from 1A to 2A, velocity will be a function of pressure, it is the same streamline, 1A going to 1A to 2A. If you go from 1B to 2A, it crosses perpendicular streamlines. Okay. If you go from 1A to 2B, it does not cross the streamlines. Going from 1A to 2A, it does not cross the streamline. In all cases, what we do not know is P1, right. So, the equation, Bernoulli's equation, P1 by gamma plus Z1 plus V1 square by 2G is constant. Okay. So, P1 by gamma plus Z1 is going to be, we can set it as 0, okay, at point 1, and because this is exposed to atmosphere, we can assume to be 0, and because this has reached at the top, what happens is there will be no velocity, right, because the water will rise until the maximum, that it can, and there the velocity will be 0. So, we can simply write V1 square by 2G. So, the velocity that is there will be equal to 2G Z2, or V1 is 2G Z2. So, this is the velocity, or if we know the velocity there, we can estimate Z2. Okay. That is how the water is going to rise in the stagnation tube. Now, there is another thing, pipette tubes, which is used to measure the flow velocities in an aeroplane as well. So, this is how a pipette tube looks like. Okay. It is used to measure airspeed on aeroplanes. It's very old technique, but still very successfully this is used for measuring the airspeed on an airplane. It can connect a differential pressure transducers to measure the V square by 2G, because Bernoulli's equation has V square by 2G. So, what it does is measures V square by 2G and therefore tells the air speed. It can be used to measure the flow of water in pipelines also, pipette tube. So, this is something like this, it looks something like this, okay, in an aeroplane. So, this is fixed in the aeroplane. Okay. All right. So, this is, it shows how many knots are there. Okay. I mean the typical panel of the aeroplane speed. And important thing to note is this is a point measurement, because Bernoulli principle is applied at different points along a streamline. This is important to note. All right. So, pipette tube. So, there is a velocity V, there is point 1 here and point 2 here. So, connect two ports to a differential pressure transducers, make sure that the pipette tube is completely filled with the fluid that is being measured. Solve for velocity as a function of pressure difference. This is stagnation pressure tap, this is static pressure tap. So, what it does is it measures pressure at point 1, at point 2, okay, and okay. So, the Bernoulli's equation says P1 by gamma plus Z1 plus V1 square by 2G is constant. So, here Z1 is 0 at point 1, okay, we assume that is the datum, and the because it is stagnation point, the velocity at 1 will also be equal to 0, all right. Because this is also at the point 2 is also here where datum is 0, that Z2 is also equal to 0, okay. So, V1 is 0 and Z1 is equal to Z2, that is why we have done this, okay. So, V that is measured here is a difference of pressure, and equal to V is equal to, using this equation we get this, and P1 and P2 are measured using this pressure transducers. Okay. So this is how the pipette tube works or functions. So there are some relaxed assumptions for Bernoulli's equation. I mean, ideally Bernoulli's equation should be applied for the assumptions that we had discussed a couple of slides ago, but there could be some relaxed assumptions for Bernoulli's equation. For example, frictionless, that the velocity is not influenced by viscosity. So there is, if the flow is not frictionless, there will be some energy loss. Accelerating flow, for example, at short distances, there we can apply a steady flow, or we can also use gradually varying flow. Okay. Constant density, incompressible. So if we have very small changes in density, then also we can apply Bernoulli's equation. This will not be exact, but okay, approximately equal. And we have to use it along a streamline, but this cannot be relaxed. We cannot cross a streamline because the constant C will change, and therefore Bernoulli's equation will no longer be valid. So another concept is Bernoulli's equation normal to the streamlines. We have seen along the streamline, now the other is normal to the streamline. So we have seen this in the previous, when we were dealing with the Bernoulli's equation along the streamline. So similarly we can write minus the force equation, we can write minus delta P by delta N plus rho An plus rho G dz dN. Here An is V square by R, where R is the local radius of curvature. Okay, N is towards the center of the radius of curvature, and this is equal to 0. S is constant along this streamline. So therefore, proceeding in a similar way, we obtain dP is equal to del P del S into ds plus delta P delta N into dN. You remember we had the same along the streamline. ds is equal to 0, right, because and we can write dP dN is equal to del P del N. Alright. So what happens is we get minus dP dN is equal to rho V square by R, okay, plus rho G dz dN. Okay. Alright, because we can write delta P delta N is equal to, and we obtained this from this. So this equation becomes this. Alright, the same procedure, no changes whatsoever. So this is the equation. We are not going into too much detail about this, but this is how you can have the Bernoulli equation normal to the streamline. So you see, when you integrate this, this will have a different consequence. So now the Bernoulli's equation applications. One is stagnation tube that you have already seen. The other was pipette tube, which we discussed. The free jets equation we have seen. We have not seen orifice, but orifice is one of the other areas where Bernoulli's equation is there. Venturi meter. The Bernoulli's equation is applied across sluice gate and sharp crested weir. Okay, this is how a Venturi meter looks like. This is how a sluice gate. So these actually are all practical places where Bernoulli's equation can be applied. So I'll take this one. and these are applicable to the contracting streamlines, accelerating flow. One of the examples, as I said, we had not seen was Venturi meter. How would you find the flow Q given the pressure drop between point 1 and 2 and the diameters of the two section? You may assume the head loss is negligible. Draw the EGL and HGL over the contracting section of the Venturi meter. So, this is the Venturi meter, alright. The water will rise depending upon the pressure. How many unknowns? What equations are we going to use? Those are the questions. Okay, so the first thing that we can do is we apply at 2 points we apply the Bernoulli's equation, all right. So we take the pressure P1 P2 on one side, Z1 is equal to Z2, okay. So that will be P1 by gamma minus P2 by gamma is equal to V2 square by 2G minus V1 square by 2G. As you see, the point 1 and 2, the datum is same, right. That is why we were able to cancel this one out. And Q is equal to velocity into area. V1A1 is equal to V2A2. So V1 pi D1 square by 4 is equal to V2 pi D2 square by 4. Alright. So V1 D1 square is equal to V2 D2 square, just continuing with this thing. So V1 will be equal to V2 D2 square by D1 square. Normally we know D1 and D2. So there is a relationship obtained between V1 and V2. So putting V1 in terms of V2, so we can, instead of V1 obtained from here, we can put here, and therefore we can get this equation here. Now, therefore on writing V2 we can get 2G P1 minus P2 gamma 1 minus D2 by D1 to the power 4 and Q, simply we multiply this with V1A1. Okay, we have this term CD, that is for practical problems, and I know practical problems there is a coefficient that you determine in experiments, but anyways this is the theoretically this is the main method. Okay, P1 and P2 you can obtain from how much the fresh water has risen into the, all right. So this is a question: water flows up a tapered pipe as shown in figure below. Find the magnitude and direction of the deflection H of the differential mercury manometer comprising to a discharge of 120 liters per second. The friction in the pipe can be completely neglected. I think we should stop the class for today now and resume our next class by solving this practice problem. Thank you so much. See you next class.